Going straight in, there's already a set way of representing statements, and that is with the use of certain symbols or denotations. To represent a simple statement, you use a capital letter. And to clarify, a simple statement, by definition, contains no connecting words, such as either or, and, if, then, and if, and only if. These four connecting words are called logical constants. Now, to represent these logical constants, we use the following symbols. The dot, much like a bullet, represents the connecting word and. This can be called conjunction. The small v is used to represent the connecting word either or. This is called alternation. The short arrow symbol is to present the connecting word if, then. This can be called conditional. Finally, the three lines, much like an equal sign with an extra line, represents the connecting word if and only if. This is then called biconditional. Again, statements either contain connecting words or not. Statements without them, however long they may be, are simple statements that are represented by single capital letters. Let's consider these statements as examples to further clarify this description. Brothers are male siblings. This is a simple statement. Notice how it does not contain connecting words. Provided that it is only a simple statement, we can use one of the 26 letters of the alphabet. It can be the capital letter B, or it could be any other capital letter like Z, Y, X. Here are other examples with their corresponding capital letter to represent them. Once you use a letter to represent a simple statement, the content can disappear, as the letter is understood to hold the simple statement already. Compound statements, on the other hand, are statements that have connecting words. Basically, two simple statements are connected by connecting words. To easily understand, let's put it into practice. We have two simple statements represented by their own capital letters. Plato is a philosopher represented by the capital letter P, and Aristotle is a philosopher represented by the capital letter Q. It can now be understood that we're talking about these two statements, but only with the use of letter P and letter Q. In the matter of representing compound statements, we'll make use of these two simple statements to elaborate the different representations, starting with conjunction. P dot Q. This reads P and Q, since dot is the technical symbol of conjunction, and you know that conjunction is the technical representation for the and connecting word. This is then how we represent a conjunction to reveal its logical structure. P dot Q then takes the place of the compound statement. Plato is a philosopher and Aristotle is a philosopher. Or to shorten it, Plato and Aristotle are philosophers. Now, instead of a conjunction, let's use the alternation symbol V. P, V, Q. This reads either P or Q, since V is the technical symbol for alternation, and alternation is the technical representation for the either or connecting word. We can do the same for conditional. P, short arrow, Q. This reads if P, then Q, or simply P, then Q. Since the short arrow is the technical symbol for conditional, and conditional is the technical representation for if, then, and biconditional, P, Q. This reads P if and only if Q, since this symbol is the technical symbol for the biconditional, and biconditional is the technical representation for if and only if. Like the different connecting words that have their respective symbols to represent them, negation also has its own, which is the tilde symbol. For example, let us negate a simple statement, R. This can be then represented as not are. Simply put, to negate a statement, you use the tilde symbol before the statement, and it is then understood that it means not statement. We can negate both simple and compound statements. However, in negating compound statements, it does not simply mean not. Rather, it can be stated as it is not the case that. And if this phrase becomes redundant, we can use the phrases it is false that or it is not true that. To negate an entire compound statement, we bracket the compound with parentheses in order to mark the scope of the negation to avoid confusion. To negate a certain element of the compound, on the other hand, you must remove the parentheses and directly use the tilde symbol on the element that you wish to negate in the compound statement. You can do the following. This reads if not P, then Q. Or in the case of negating both elements, this reads if not P, then not Q. However, if you negate the compound together with its negated elements, you have to bring back the parenthesis. This then reads, it is false that if not P, then not Q. Moving on, we will now study the truth values of compound statements. In this module, we'll first apply the three principles of truth discussed in previous units. The principle of identity. It's rather self-explanatory. It states that a statement implies itself. Suppose that will represent a simple statement. Puppies are young dogs by the capital letter of P. And let's assume that puppies are indeed young dogs by definition. So, if P is true, then P is true. Alternatively, if puppies are not young dogs, then if P is false, then P is false. Therefore, this statement is always true, a tautology, which means that the truth value of a statement is retained indefinitely over time. Much like how it was previously discussed, this principle guarantees that the truth value of any statement is either true or false only. It does not consider the probability values. Still using the simple statement, puppies are young dogs, and represented by the capital letter P, let's try and understand this principle in representation. This is read as either puppies are young dogs or they are not. Following the principle of excluded middle, and suppose that P is indeed true, then we automatically suppose that its negation, not P, is false. There is a technical name for this relationship. It's called truth functional relation, which basically means that P and not P are truth functionally related. Alternatively, we can consider the reverse. If the affirmative P is false, then its negation, not P, is true. The principle of non-contradiction. To simplify, also still with the use of the same statement, P cannot be both true and false at the same time and in the same respect. P can be true in one situation and false in another, but they cannot be true and false at the same time. So, puppies cannot be both young dogs and not young dogs at the same time, and in the same respect. This can be represented as P dot not P, contradicting hence the concept of principle of non-contradiction. To make it right, it must be in this representation. This is read as, it is not the case that P and not P, which is the nullification of the previous representation. Just in the module before this one, I've introduced the technique of negation. Now, we'll use it in application to a more complex level. But to easily understand, we'll talk in tables. As you can see, the table reflects the following truth functional relationship. If P is true, then not P is false, or if not P is true, then P is false. Either way, we know that from this, P cannot be both true and false therefore this would be a violation to the non-contradiction principle. However, it doesn't simply end there, because we also have what we call double negation, which is quite literally negating twice, denying a statement twice, which actually implies its affirmation. As an example, it is false that puppies are not young dogs. This is a simple statement that can be represented as not P. By analyzing the statement, it can be said that not P is equivalent to P. You might think that if there is a double negation, can there be triple and quadruple? Yes, as hard as it may seem and believe. If a statement is negated 3 times, it only denies it. If it's negated 4 times, it only affirms it twice, much like in double negation, just twice again. Let's move on to the truth values of compound statements, true logical constants: conjunction, alternation, conditional, and biconditional. First, we'll consider the representation of a conjunction, P and Q. Note that P is true and F is false. Here's a table representation for determining the logical form of this compound. As for the example, P and Q is only true provided that both P and Q are true. Conjunction set of premises is only true when all its elements are true. If one or both is false, then the whole premise set is false. We will now consider the representation of an alternation, either P or Q. P and Q are called alternates. In this table, notice the shaded row. Both its alternates are false, which points out how an alternation is false only when both alternates are false. So to formulate a true alternation set of premises, only one of its elements should be true. Now let's consider the representation of a conditional. If P, then Q, or simply P then Q. Here, P is called an antecedent, while Q is called a consequent. Directly using the example, the shaded row shows when a conditional is false. It is when P, the antecedent, is true, and Q, the consequent, is false. All other combinations of these show that the conditional is true. Right now, what you see here is a table showing the validity in judging arguments. Most logicians will agree that the logical form of all deductive arguments is logically isomorphic with the logical form of the conditional statement. Focus on the table presented, specifically on the shaded one, which is concluded to be invalid. Notice how the argument is invalid only when the premise set is true and the conclusion is false, much like when a conditional statement is false, namely when the antecedent is true and the consequent is false. This only means that the table of validity is logically isomorphic with the truth table of a conditional statement. Moving on to considering the representation of a biconditional. P if and only if Q. Notice how 2 rows are shaded. This points out that biconditional is true under 2 conditions. One is when both elements are true, and 2 is when both elements are false. Otherwise, the biconditional is false. Finally, negating compound statements. Much like the representation of negating simple statements, the use of the tilde symbol also extends to here. Simply put, this table here applies to all of the other compound statements. Just recall that we have adopted the convention of affixing the tilde symbol to the representation of a simple statement to constitute its denial.
We're now diving into Module 4, Representing Arguments. In this module, we'll dive into why representing arguments is crucial for determining their validity. To accurately judge an argument's validity, we need to separate its logical structure from its content. Let's explore how this process works and how it forms the backbone of logical analysis. When we represent an argument, we aim to isolate its logical structure, making it possible to focus solely on the form rather than on the specific content. This approach lets us apply methods, such as the truth table method, to test the validity of an argument. We can represent any argument just like we represent a statement, whether it's simple or compound. By isolating the logical structure, we can gain two benefits. Firstly, to reveal the argument's logical form, and secondly, we separate it from its content, making it easier to determine validity. Let's break down the steps in representing an argument. First is to identify simple and compound statements. For instance, if we can represent statements, then we can represent arguments is a compound statement. We can represent statements, and therefore we can represent arguments are simple statements. The second step is to assign letters to premises. In our example, the word represent gives us the letter S for statements and letter A for argument. The third step is to use the conclusion indicator. We represent the conclusion with 3 dots, like so. The fourth step is to reveal the logical structure. Once we structure the argument vertically, it should look like so, leading to the logical conclusion. This structure helps us analyze if the argument follows a valid form. Here's another example. The compound statement, if we study logic, then we improve our reasoning power. And then the simple statements, we study logic, and therefore we improve our reasoning power. When represented, it becomes like this, where S represents study and R represents reasoning. This form is known as modus ponens and is valid since it follows a consistent logical pattern. Content isn't part of the analysis of validity. Instead, validity depends on the logical form. For instance, an invalid argument form might look like this. The compound statement, if we study logic, then we improve our reasoning power. And the simple statements, we improve our reasoning power, and therefore we study logic. So this form will be represented like so, which becomes invalid because it assumes the outcome guarantees the initial condition. This error is called the fallacy of affirming the consequent. By using logical structure, we can analyze arguments without being influenced by content, focusing on pure reasoning. This approach is foundational for analyzing and proving validity in deductive arguments. Understanding these structures empowers us to judge arguments on their logical merits alone, ensuring that no true premise leads to a false conclusion. Moving on to Module 5, Basic Deductive Argument Forms. In this module, we'll explore fundamental argument structures that help us distinguish between valid and invalid forms, even in more complex arguments. Mastering these basics allows us to understand and evaluate the logical structure of any argument, especially when dealing with conditionals. Let's begin with conjunction, where two true statements are combined to create a single true compound statement. For example, amphibians are animals, and birds have feathers. Using the letters A for animals and B for birds, we can represent this like so. By joining these two true statements, we preserve the truth value of the conjunction. Similarly, with simplification, we can separate a conjunction to infer the truth of each individual statement. For instance, from the conjunction A and B, we can validly infer either A or B alone. Now let's look at alternation, where two statements form an either-or relationship. For example, with whales are mammals or snakes are reptiles. Represented with W for whales and S for snakes, it becomes represented as so, with the logic leading to the logical conclusion that therefore either whales are mammals or snakes are reptiles. Alternation remains true as long as at least one of the statements is true. However, unlike conjunctions, we cannot infer any one of the statements alone from an alternation. Adding an alternative is another valid form. For example, Kiko Pangilinan is running for Senate is true, while Leni Robredo is running for Senate is false, leading to the logical conclusion that, therefore, either Kiko Pangilinan is running for Senate or Leni Robredo is not running for Senate. Remember that an alternation is valid as long as at least one part is true. If both statements are false, then the alternation is also false. Now, adding a conjunct is different. If a single statement is true, you cannot simply add another unrelated statement as a conjunction, since it may invalidate the argument. The form is invalid unless both statements hold true, so we should only form a conjunction when we are certain that both statements are true. Disjunctive syllogism is a valid argument form for detaching one alternative when we know at least one part of the alternation is false. We start with the statements Kiko Pangilinan is running for Senate and Leni Robredo is running for Senate. Both statements will be represented by the letters K and L respectively. If we know that L is false, we can validly conclude that K must be true. The key is understanding that disjunctive syllogism works when at least one part of the alternation is false, ensuring the truth of the other. This leads to the logical conclusion that therefore Kiko Pangilinan is running for the Senate. Lastly, let's look at denying an alternative, which often gets confused with disjunctive syllogism, but is actually invalid. For example, if we know that Kiko Pangilinan is running for Senate is true, it doesn't logically follow that Leni Robredo is not running for Senate. Since it's possible for both alternatives to be true, we cannot assume one is false just because the other is true. Avoiding this mistake is crucial for accurate argument analysis. By mastering these basic argument forms, we gain the tools needed to handle more complicated arguments in logic. Always remember to analyze the structure carefully to distinguish valid forms from invalid ones.
And you're now here on Module 6, which is complex argument forms. There are 11 complex argument forms on Acuña's philosophical analysis. Before we dive into these 11 complex argument forms, first things first, a statement does not equal to a premise, because the premise is the whole sentence or the whole argument. Meanwhile, an argument structure is the graphical depiction of the number of premises and the conclusion, as well as they reveal the type of statements used here. Now introducing the first complex argument form, which is modus ponens. This is where the second premise affirms the antecedent, which is usually the first statement. Its argument structure implies that if a statement is true, refer to premise 1, and a second statement or premise 2 implies the first statement or premise 1, then this second statement must also be true. Affirming the antecedent is the valid argument of modus ponens, and the reverse of this is an invalid argument, which is the fallacy of affirming the consequent, which is usually the conclusion. Moving on to the counterpart of the valid form of modus ponens, which is modus tollens. Its valid form is denying the consequent, which is also the valid argument of modus tollens. This is an if-then statement, followed by a negation of the then statement, and its invalid argument form is the denying of the antecedent, which is the last example on the slide. Now, let us move to more valid argument forms. A hypothetical syllogism is also a valid argument, as well as a constructive dilemma, which is a valid argument or logical form that is a combination of two modus ponens. This is valid because it affirms the antecedents of both conditionals on the second and third premises, making it valid to conclude the consequent in the conclusion or fourth and last premise. The third argument form in the slide is called a destructive dilemma, which is also a valid argument form that is a combination of two modus tollens, meanwhile. This is valid because it denies the consequent of both conditionals on the second and third premises. Therefore, we can validly conclude the denial of the antecedent in the conclusion. Now, we're down to the last 4 complex argument forms, which are more invalid arguments. The first one on the slide is called detaching the consequent. This is another invalid argument because you cannot conclude the consequence from a conjunction. Even if a conjunction's antecedent is true, it doesn't necessarily or automatically mean that the conjunction's consequence is also true. Then we also have the fallacy of misplaced middle, which should not be confused with hypothetical syllogism. We also have pseudo-dilemma 1 for these invalid arguments, which might seem like it's valid, but upon closer inspection, it's actually not because it's a fallacy. This fallacy denies premise 1 and 2's antecedents, therefore, it cannot conclude the denial of both the consequence of premise 1 and 2. If the argument denied the consequent, it can be concluded by denying the antecedent. This is actually destructive dilemma, so we should not confuse this with pseudo-dilemma 1. And finally, we have pseudo-dilemma 2, which is also an invalid argument form, so we should not confuse these with valid arguments because pseudo-dilemma 2 does the opposite from pseudo-dilemma 1 by affirming the consequence of premise 2 and 3, making the antecedents non-affirmable. If the argument affirmed the antecedent, it could have had the conclusion of the consequence being the ones affirmed. This is a valid argument called constructive dilemma, so we should also not confuse pseudo-dilemma 2 with this. We should also remember the norm. A valid argument is always when we affirm the antecedent or deny the consequence of a conditional. And now we're down to the last module of Unit 3, which is Module 7, the truth table method. That's so many T's. So basically, this will teach us how to apply the technique of determining the validity or invalidity of any argument form, such as the complex argument forms we just tackled back in Module 6. Take note that the logical form of an argument refers to its truth table and not its argument structure. The argument form is valid if the truth table of an argument does not have a case where the premise set is true and the conclusion is false. The first step of this method is to represent the given argument in horizontal form. And then for the second step, we count the number of simple statements in the argument. In this argument, there are 2 in the given example, which are A and C. For the third step, we make a table for all possible substitution instances of the truth values of A and C. Also, take note that we double the number of rows each time a statement is added, such as if you have 3 statements, such as A, C, and Q, the table you'll make will therefore have a total of 8 rows. This also means that 4 statements make 16 rows, 5 makes 32, 6 makes 64, 7 makes 128, and 8 statements make 256 rows, and so on. And finally, for the fourth step, after completing the table of substitution, we assign the truth values to the statements in argument structure.